Hi students, today we are going to continue with your topic thermodynamics and this is your fourth lecture. Today we are going to start with the thermodynamic states, thermodynamic state variables and equation of states. Here you can see that in the boxes which are given in your screen that thermodynamic systems which are in equilibrium state are described by some spatial values of macroscopic variables which is called as state variables. Means if thermodynamic state is not in the equilibrium, you cannot describe it in the state variables. You have to confirm that whether system is in equilibrium, that is thermodynamic system is in the equilibrium or not. If system is in equilibrium, then you can describe that thermodynamic system in the form of state variables. Okay, then which is that state variables? If you are considering a gas, it is not mixture, only a pure gas, then you can describe it by pressure, temperature, volume, mass, number of moles, etc. But in case of mixture of gases, for example, you can consider automobile engine in which along with pressure, temperature, volume, mass, number of moles, its composition. किसका composition? जो भी mixture of gases उस engine में है या फिर आपने use किए हैं उसका composition भी required है to describe its state. Then when system is not in equilibrium, we cannot describe it in terms of state variables. For example, you can consider bursting of inflated balloon, which you have studied in earlier lectures that inflated balloon इसका example है टायर. टायर में जो ट्यूब है in which air is filled under certain pressure or you can say high pressure, that is called as inflated balloon. If that tube of tire breaks or burst, then what will happen? Air inside that tire suddenly get expand to the atmosphere. Due to this expansion, pressure of air is not uniform everywhere. So, this system is not in equilibrium and we cannot describe its state in terms of state variables. Also, you can consider another example is that fuel inside the cylinder of automobile engine undergoes an explosive chemical reaction after ignition. So, such a system also cannot be in the thermodynamic equilibrium or an equilibrium state. So, you cannot describe such a system. You cannot describe such a system in terms of state variables. In other words, you can say that thermodynamic state variables describes the equilibrium state of the system. Now, state variables are not always independent. So, mathematical relation between the state variables is called as equation of states. इसका एग्जाम्पल है आइडियल गैस इक्वेशन. where V is the volume of gas, P is the pressure, N is the number of moles of gas, R is the gas constant, and T is the temperature of ideal gas, then PV is equal to nRT. This is ideal gas equation. If for some experiment or for some thermodynamic system, if we are taking fixed amount of gas, then gas constant R and N, number of moles of gases, is constant for that fixed amount of gas. So, if we kept temperature of such a gas is constant, then pressure and volume of that gas will change. If we kept pressure of that gas is constant, then temperature and volume of that gas will change. And if you kept volume of that gas constant, then pressure and temperature of that gas will change. Now, this is the PV diagram of ideal gas equation at constant temperature, or you can say graphical representation of equation of states of gas of system. ओके, इस पीवी डायग्राम को आप बोल सकते हो पीवी डायग्राम, पीवी कर्व, इंडिकेटर डायग्राम ऑफ सिस्टम फॉर एन आइडियल गैस at constant temperature. Okay, then the PV diagram, which is drawn at constant temperature, or PV curve at constant temperature, is called as isotherm. PV diagram for real gases have more complicated equations or equation of state. Hence, its PV diagram is also complicated. So, equation of state of thermodynamic system and PV diagram is useful in studying behavior of real gas. Now, you have seen this equation in first law of thermodynamics, where W is work done. If some system is changing its state from initial to final, or its volume from initial to final, and pressure of that system is constant, then work done of that system is given by equation integration of limits Vi to Vf P into dV. If we can evaluate this integral, then we can know the relation between pressure and volume, or path between the limits of integration. Now, on your screen, you can see that the pressure and volume curve of ideal gas when temperature of system is constant. Here, we will consider that a gas is confined in a cylinder with movable, frictionless and massless piston. In first figure, you can see that from path 1 to 2, expansion of gas takes place from volume V1 to V2, and pressure of gas decreases from P1 to P2. Here, volume of gas increases from V1 to V2. When volume of gas is V1, pressure is P1, and when volume of gas is V2, pressure of gas is P2. Here, pressure decreases and volume of gas increases, and due to this volume of gas changes due to outward displacement of piston. As you have seen the diagram of cylinder in which gas is confined along with piston, then if piston is displaced in outward direction, then there is a work done by the gas on piston, and this work done we are considering as positive value, and work done can be calculated by the formula, that is integration of limits v1 to v2 p dv, or you can say area under the curve. Here gas has done work on the piston, and due to this we are considering this work done as positive, and value of this work done is always greater than 0 in first case, or in first figure, or in case of first figure where volume increases, and due to that work done is positive. In second figure you can clearly see that from system changes from point second to point 1 or point 1 to 2. Here pressure of system or pressure of gas changes from P1 to P2, that is pressure increases, volume decreases. From path 1 to 2, volume of gas changes from V1 to V2. Compression of gas takes place, that is volume of gas decreases. As you can clearly see from the figure that V1 is greater than V2, and path is changing from, system is changing its path from 1 to 2, where volume of gas decreases, means there is a compression of gas takes place, and here pressure of gas increases from P1 to P2. Now here there will be the inward displacement of the piston, means what we have did, we have pushed piston inside the cylinder. So what we have did, work done on the gas, and due to that this work done is negative, that is you can calculate work done by formula work done is equal to integration of V1 to V2 P dV, which is always negative. Here work done is on the gas, so work done will have negative sign, or you can find work done by another way, that area under the curve. Now in third diagram you can see that from path 1 to 2 pressure of gas is constant, and volume of gas increases from V1 to V2. Here work done is constant and positive. We can calculate work done by the formula P into V2 minus V1, which is greater than 0, or work done is equal to the area under the curve. Now for any thermodynamic system or process, if volume of gas is constant, then there will not be any work done. So work done will be 0 due to no displacement of gas, you can say, or piston. So Here is the sign conventions of work done again, that when volume of gas increases, there is a positive work done. When volume of gas decreases, negative work done. When volume of gas increases under constant pressure, positive work done. In first figure, pressure decreases, positive work done. Pressure increases, negative work done. When pressure is constant and volume is changing or increasing, there is a positive work done. Now we will study what is meant by thermodynamic process. The process or method by which the initial state of the system changes to its final state. This is called as thermodynamic process. Here, exchange of energy from system to the environment, we can take it as a negative, that is minus Q, which you have studied in earlier lecture, that when system loses its energy, then amount of energy transferred from system to the environment is negative. And when exchange of energy takes place from environment to the system, we can consider it as a positive Q, that is system gains energy from environment to the system. Here we can take that value as positive. Now in terms of work done, when work done by the system is positive and work done on the system is negative. Changes in the initial thermodynamic state to the final state should be too much slow. So system should be always in the thermodynamic equilibrium. That is, if you want in the any process, system should be in the thermodynamic equilibrium, then changes which is happening in that system to change that system from initial state to the final state should be too much slow. That is, you can call it as a infinitesimally slow. Then and then only system can remain in the thermodynamic equilibrium. Due to this changes in the state variables also occurs very slowly. अगर सिस्टम बहुत स्लोली इनिशियल स्टेज से फाइनल स्टेज में जा रहा है या इनिशियल स्टेट से फाइनल स्टेट में जा रहा है, तो उसके जो स्टेट वेरिएबल्स हैं जिसमें हम सिस्टम डिस्क्राइब करेंगे, उनमें भी बहुत स्लोली चेंज आएगा. एंड सच अ सिस्टम इज कॉल्ड एज quasi-static system. Change in the initial state to the final state can have many intermediate states, which is as shown in figure. In figure, you can see that system changes itself from initial state A to final state B by 3 different ways. In first part, you can consider system changes from initial to final state directly. But in second and third case, there is a intermediate states are present. That is, in case of second part, system will change its initial state A to first C and then final state to B. Means C is the intermediate state of path second. And in case of third path, D is the intermediate state between A and B. So, in the first path, here we have took three paths together, and in next three figures we have changed, or we have considered individual diagrams of three paths. That is, first path is A to B. Then what is the changes in pressure and volume of the gas when temperature is constant, that we will study. In case of first path, system changes from A to B. Then its pressure decreases from Pi to Pf, and volume increases from Vi to Vf. As we have studied earlier, when pressure decreases and volume increases, work done by the system is positive, and that work done we can calculate by area under the curve. Now, in second path, you can see that A is the initial state of the system, B is the final state of the system, and C is the intermediate state. In path 2, first system will change itself from A to C, where volume of that system increases and pressure is constant. Now, in second case, after C, volume of the system is constant, which is Vf, and pressure decreases from Pi to Pf, or you can say that after Vf, pressure of gas changes or pressure decreases at constant volume. In such a case, we can calculate work done as area under the curve. Now, in case of third path, where A is the initial state, B is the final state, and D is the intermediate state. From A to D, pressure of gas decreases with constant volume Vi, and from D to B, volume increases with constant pressure. So, work done is again area under the curve. So, you have studied that system can change its state from initial state to final state very slowly. Why slowly? To maintain its equilibrium state. If system changes initial state to final state immediately, then that system cannot be in the equilibrium. If system changes its state from very slowly, then state variables also changes very slowly or infinitesimally slowly, and system can change its initial state to final state between many intermediate states. That is, change in initial state to the final state can have many intermediate states, which you have seen in this process. That what is meant by thermodynamic process? Method or process by which system changes its initial state to the final state, and it can be in various paths, and if path changes, its work done also changes, yet its initial and final states are same. In case of first diagram, it take direct path from A to B and its work done is different. If it takes the intermediate states, as in second figure it's C and in third figure it's D. So work done in both the cases will be different. So in thermodynamic process, how system changes itself from from initial state to final state, or the process by which we can change system into initial state to the final state, and which path system will take depends on that its work done also changes. Now we will see heat added during thermodynamic process. Thermodynamic state of the system can be changed by adding heat as well. Now in figure 1 you can say that there is an isothermal expansion of gas. What is meant by isothermal expansion we will see in the next lectures. And system does work on the piston. So in first diagram what you will see that position of piston is different, that is piston is displaced in outward direction. When you can apply, or when we have applied a heat to the system, and volume of gas increases and pressure will get decreased. Here work done is positive and system gains the energy, and due to that Q, that is amount of energy added to the system, is positive. So in first diagram you can see that isothermal expansion of gas. System consists of an ideal gas confined to a cylinder with massless, frictionless, movable piston. Same amount of gas is filled in both the containers. Both the container means in figure फर्स्ट एंड सेकेंड, यहाँ पे दो बॉक्सेस है. फर्स्ट बॉक्स में जितना गैस हमने फिल किया है उतना ही हमने सेकेंड बॉक्स में और सिलेंडर में भी फिल किया है. गैस इज हीटेड स्लोली इन कंट्रोल्ड मैनर. सो जब गैस हीट होगा तो क्या होगा, गैस एक्सपांड इन कांस्टेंट टेम्परेचर. मतलब आपको हीट इतनी स्लो देनी है दैट whatever the heat we are providing, it is used to change the volume of gas and its temperature remain constant. If Vi is the initial volume of the gas, then after expansion Vf is the final volume of gas. Here system absorbs finite amount of heat, and due to absorption of heat, work done is positive. Why work done is positive or greater than 0? That is, expansion of gas takes place, volume increased, and work done by the gas on the piston. And Q is again positive. It is because gas has absorbed or gained energy. Now here in second diagram you can see that uncontrolled expansion of gas. In फर्स्ट सिलेंडर आपको क्या दिख रहा है, एक्स एंड वाई सेपरेट कंपार्टमेंट्स दिख रहे हैं. ठीक है, एक्स में टोटली गैस फील्ड है, वाई में वाई एम्प्टी है. ठीक है, हियर एक्स का वॉल्यूम है वी आई, एक्स में जो गैस भरा हुआ है उसका वॉल्यूम है वी आई, एंड वाई का वॉल्यूम है वी आई डैश. जो फाइनल वॉल्यूम आपको मिलेगा वो होगा VF विच इज इक्वल टू VI प्लस VI डैश। ठीक है, और X और Y दोनों में क्या है, कंपार्टमेंट है या पार्टीशन है। ठीक है, जो ब्रेकेबल है या फिर बहुत ही थिन पार्टीशन है। तो X में टोटली गैस फील्ड है, Y में कुछ नहीं है। कुछ रीजन की वजह से इफ partition between X and Y get broken, तो क्या होगा, there will be the uncontrolled expansion of gas। तो सिर्फ क्या हुआ, पार्टीशन ब्रेक हुआ, हमने बाहर से कोई एनर्जी प्रोवाइड नहीं की। ठीक है, आपको यहाँ पे क्या दिख रहा है, इंसुलेशन। तो अंदर से बाहर कोई एनर्जी ना जा पाए या बाहर से कोई अंदर ना जा पाए, इसलिए हमने क्या किया है, उस सिलेंडर को क्या किया है, इंसुलेट किया है। ठीक है, सो देयर विल नॉट बी एक्सचेंज ऑफ हीट और वर्क डन फ्रॉम द सिस्टम टू द एटमॉस्फेयर, और यू कैन से environment or environment to the system. Such a expansion is called as free expansion, and इसका एग्जाम्पल ऑलरेडी मैंने बहुत बार बताया आपको, abrupt puncturing of inflated tire और balloon। abrupt मतलब sudden, puncturing of inflated tire। Heat transfer to a system also depends on its path. Now we will study in next lecture, that is classification of thermodynamic processes. Thermodynamic states can be described by its pressure, volume and temperature. Thermodynamic state can be described by variables, for example pressure, volume, temperature, mass, which you have studied already. Process by which two or more of these variables can be changed is called as thermodynamic process. Thermodynamic process में आपने क्या पढ़ा, the process by which system can change from initial state to the final state. तो अगर सिस्टम इनिशियल स्टेट से फाइनल स्टेट में चेंज हो रहा है, मतलब क्या है, अगर आपने प्रेशर कांस्टेंट रखा तो उसमें टेम्परेचर और वॉल्यूम में चेंज होगा। अगर आपने टेम्परेचर कांस्टेंट रखा तो उसमें वॉल्यूम और प्रेशर में चेंज आएगा। अगर आपने वॉल्यूम कांस्टेंट रखा तो प्रेशर और टेम्परेचर में कुछ चेंज होगा, तभी तो सिस्टम इनिशियल स्टेट से फाइनल स्टेट में जाएगी। देयर आर number of different ways to change state variables, or you can say there are different thermodynamic processes by which we can change state variables। मतलब क्या है, आप बहुत सारी तरीके से क्या कर सकते हो, थर्मोडायनेमिक प्रोसेसेस से सिस्टम की स्टेट चेंज कर सकते हो। ठीक है, फॉर आवर कन्वीनियंस हम क्या करते हैं, एनी वन ऑफ द स्टेट वेरिएबल इज हेल्ड कांस्टेंट एंड अदर टू आर वेरिड। जैसे मैंने आपको बताया, टेम्परेचर कांस्टेंट रखेंगे, प्रेशर और वॉल्यूम का स्टडी करेंगे, देन प्रेशर कांस्टेंट रखेंगे, वॉल्यूम और टेम्परेचर का स्टडी करेंगे, वॉल्यूम कांस्टेंट रखेंगे, प्रेशर और टेम्परेचर का स्टडी करेंगे, या फिर वॉल्यूम, टेम्परेचर, प्रेशर में एक चीज़ आपको कांस्टेंट रखनी है, दूसरे दो को चेंज करना, एंड ड्यू टू दैट आपको क्या मिलेगा, चेंज इन द थर्मोडायनेमिक सिस्टम फ्रॉम इनिशियल स्टेट टू द फाइनल स्टेट। एंड इन योर syllabus these are some processes which we are going to study in next lecture, that is reversible and irreversible process, isothermal process, isobaric process, isochoric process, adiabatic process, cyclic process and free expansion. So this is about your fourth lecture, and in next lecture we will start with the reversible and irreversible process. So This is about your fourth lecture. Thank you.